Hello students, welcome to the class of Control System 2 followed by the code EE603. I am Harji, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today in this video lecture we will discuss on the controllability and observability of a given system. During this video lecture, we will discuss on the introduction, the controllability and observability with its example, and the controllability and observability after the sampling. Now, the controllability and observability are two important properties of the state models which are used to design a controller. Now, the controllability deals with the possibility of forcing the system to a particular state by application of the control input. Now, if a state is uncontrollable, then no input will be able to control that state. So, the concept of controllability and observability are closely related to the properties of the transfer function. In other hand, when the initial states can be observed from the output is determined by the observability property. So, if a state is not observable, then the controller will not be able to find out its behavior from the system output, and hence it will not be able to use the state to stabilize the system. So, the input-output relation is defined by the transfer function, and the properties of the transfer function is related to the concept of controllability and observability test. Next is the controllability. So we can assume that input-output relationship of any n-order system with distinct eigenvalues or the roots can be represented by the dynamical system x of k plus 1 equal to xk plus buk. Similarly, yk is equal to cxk plus duk. Now, there are two concepts of controllability. One is state controllability, another is the concept of the output controllability. Now, if we consider the state equation, then it is said to be completely controllable or the completely state controllable if for any initial state x0 and any final state xn there exists an input sequence which transfer x0 to xn within some finite time. Otherwise, this equation is not state controllable. And the system in the equation 1 is said to be completely output controllable or normally output controllable if any final output can be found out from any initial state x0 by applying an unconstrained input sequence for some infinite time n. Otherwise, this is not output controllable. So this state equation x dot is equal to x plus bu or xk plus 1 equal to xk plus buk is state controllable if and only if the controllability matrix UC, which is a matrix whose columns are actually B, the multiplication of AB, then S square B, up to a to the power n minus 1 B has the full rank, or if it is n by n matrix, then it should be the rank is equal to n. So if it is so, then the system is completely state controllable. And this method was described by Kalman. So it is also known as the Kalman's method. So let us take one example. Here one matrix is given and we have to find out is it completely state controllable or not. So the system matrix is 0 1 0 0 0 1 minus a0 minus a1 minus a2, and B matrix is 0 0 1. So to first find out whether the system is controllable or not, we only need the system matrix and the B matrix. And the system matrix is 3 by 3 matrix. So the controllability matrix, it can be written as the BAB and A square B. Now n is equal to 3, so n minus 1 is equal to 2. That's why P of C, that is the controllability matrix, is B, AB and A square B. So we can write down the B matrix as the first column of the PC matrix, that is 0, 0 and 1. Then AB, we will multiply A with B, then that will be a 3 by 1 matrix, and that will be written in the second column of the PC matrix. And then A square B, so A will be multiplied with AB, then we will get the A square B, which we can write in the third column of the matrix. So the overall PC matrix or the controllability matrix, which is a 3 by 3 matrix, can be written as B, AB and A square B as the column elements. So now we need to find out the determinant of PC. So determinant of PC is equal to 1. So it means it is not of the rank equal to 3 or order of the system matrix. So the given system is controllable. Next is the observability. Now here we can see that state model, which was expressed as x dot is equal to ax plus bu and y is equal to cx plus du, is said to be completely observable if an initial state x0 can be determined from the knowledge of the output yk, and the input sequence will be k is equal to 0 to n, where n is some finite time. Otherwise, the state model is said as unobservable. So as per Kalman's, the observability matrix is written as row wise C, Ca up to Ca to the power n minus 1. So here also we will check the determinant, and if the determinant is non-zero, then the rank will be full and then the system will be completely observable. Let's take another example of finding out the system observability. Here a system is given as x dot is equal to 0 1 0 minus 2 into x, plus B matrix is given as 0 1 into u, and y is equal to c into x 0 4. So to find out the observability of the system, we need only the C matrix and the A matrix, and since A is a 2 by 2 matrix, so the observability matrix can be written as row wise C then Ca. So Ca can be found out multiplication of C matrix with A matrix, and it gives results 0 minus 12. So the observability matrix can be written as row wise 0 4, that is the C matrix, and the next row Ca matrix, that is 0 and minus 12. So if we find out the determinant of this system, so determinants becomes 0 and determinant becomes 0 represents that the observability matrix is not of the rank 2 or order of the system matrix. So the system is not observable. So to find out the controllability and the observability from a given system, we will use the method of Kalman, and first we will find out for the controllability, that is the controllability matrix, which is nothing but the columns will be represented by B matrix, AB matrix up to A to the power n minus 1 matrix. And for observability matrix, we will write the row wise the C matrix, CA matrix up to CA to the power n minus 1 matrix. Then for the both cases, we will find out the determinant of the system, and if the determinant becomes 0, then rank will not be is equal to the full order of the system matrix A, then the system will not controllable or not observable. And if the determinant is not is equal to 0, then the rank of the matrix will be full of the order of the system matrix A, then the system will be completely controllable or the observable. Next is controllability and observability after the sampling. So if we consider a continuous time system and it has been undergone with the process of the sampling, then what will be the controllability and the observability of the system? So it will be depends on the sampling period and the location of the eigenvalues of the system. So if in the presence of oscillatory modes of the system is there, then the controllability and the observability may change. Now the sufficient condition for the discrete model with the sampling period of t to be controllable when the RE of lambda I minus lambda j should be is equal to 0. That is the real part equal to 0 and the imaginary part is not is equal to 2 pi m by the sampling period. So this one is applicable for only the single input cases. And if a continuous time system is not controllable or not observable, then the discrete time version with any sampling period is not controllable or observable. Controllability and the observability also change when the pole zero cancellation will be there. So if a input output transfer function of a linear system has the pole zero cancellation, then the system will either uncontrollable or unobservable or both, which depends on how the state variables are defined. Or we can say that if the input output function does not have pole zero cancellation, then the system can always be represented by dynamic equations as a completely controllable and observable system. So we can say that we are now familiar with the term controllability and observability, and we can say that after the pole zero cancellation, the system, if the input output function does not have pole zero cancellation, it can be represented by the dynamic equation as completely controllable and observable system, which is very important because if a linear system is modeled by a transfer function with no pole zero cancellation, then it is a controllable and observable system no matter how the state variable model is derived. So therefore, depending upon how the state variables are defined and the state space representation, the pole zero cancellation due to the identical pole and zero will make the system either not state controllable or unobservable or both. Otherwise, the state space model representation can be completely controllable and observable. The controllable or unobservable modes correspond to the cancelled modes. So these are my references. I hope after this video lecture you have a clear idea about today's topic, the controllability and observability. Now we will go through some question answer session in context of this video lecture. You are requested to go through it gradually and solve it by your own. Answers are attached at the end of each question.